In this first lecture on the sequence of real numbers, we will define the concept of the sequence, look at a few examples, and then prove a few elementary results as we go on. So let us first see what is the meaning of a sequence of real numbers. It is simply a function from the set of positive integers to R. So if we denote f of n by little a n, then we can write the sequence as a1, a2, etc., an, etc. And this is the general style of expressing a sequence rather than as a function. And we will generally be using lowercase alphabet to denote the various terms of the sequence, whereby the nth term of the sequence we mean just an. So we have a1, which is the image of 1. So f1 is a1, f2 is a2, and so on. And the notation would be second bracket an with a superscript n, or sometimes, in fact, most of the times we will write in a language sequence an, so that there is no confusion that we are not talking about a set here, but just this type of a sequence. Okay, and we are saying that this is indexed by the set of positive integers, because the mapping is from the set of positive integers to R. So we have this indexing is by the set of positive integers. But in fact, we can do this by indexing can be done over any countable set. That would give you a sequence. We will not have the requirement to go into any random countable sets in general, but sometimes we will have to start a sequence with 0. So we would have a0, a1, a2, etc. And sometimes we would have a sequence which is uh, which is indexed by the set of integers. So we would have something like a minus a1, minus a2, minus a3, and so on, and then we would have a0, a1, a2, etc., so on. This is rare. We would not generally encounter such a thing, but at least starting from a0, that we will encounter. Okay, so this is just a simple definition. And what is the meaning of this? You notice, if we keep the thing in mind that this is actually a function, then it will be clear that there is a difference between what is a sequence and what is a set. Even though the notations are quite near to each other, uh, you just notice, for example, I'm writing a sequence like this: 1/2, 1/3, 1/4, etc. So nth term is 1 by n, and so on. So this means what? In the background, which we will not mention again and again, is a function which is taking 1 to 1, 2 to half, 3 to 1/3, and so on, n to 1 by n. Now what I am doing here in this second listing is I am just manipulating. I am writing half first, 1 later on, and then 1/3, 1/4, etc., 1 n, and so on. So this is also a sequence, but this is different from this sequence. So if you just think of it as a function, you notice that here 1 f is mapped to 1, but here 1 is mapped to half, 2 is mapped to 1, here 2 is mapped to half. Everything else I have left to be the same, but we could have manipulated it a little bit more also to get a more uh, to get a different example. But I think it is clear just by manipulating the first two terms to explain that this sequence and this sequence, if you look at the set is going to consist of all 1 by n, such that n is a positive integer. That is the same in both the cases. So we call that set underlying set. That is the set of all values which the sequence takes. So the values which this sequence takes and the values which this sequence takes are the same. So their underlying sets are the same. But this sequence is different from this sequence because here the first term is 1 and second term is half. Whereas here the first term is half and the second term is 1. I hope I am clear about this, that sequence is not a set. Okay, so let me just give a definition of one type of sequence first, and then we can maybe look at a few examples. So the first definition is of a bounded sequence. So naturally, with every sequence, you do have an underlying set of that. So it is the underlying set, that is the set of all values which the sequence is taking, which is different from the terms of the sequence, right? As you saw in the previous example, the terms of the sequence are these: 1/2, 1/3, 1/4, etc., 1y, and etc. Like here it is half, 1, 1/3, 1/4, etc. You could have manipulated it a little bit more, say you could have written half, 1, 1/4, 1/3, then 1/6, 1/5, and so on. So every even odd you just interchange, you get a new sequence. So this new sequence will also have the same underlying set, which is the set consisting of 1/2, 1/3, 1/4, and so on. That is the set consisting of 1 by n, where n is a positive integer. So this underlying set, we know, we call it, give it a name also, we call it the range of the sequence. Makes sense because sequence is actually a function. So we want to find out what values it exactly takes. That is going to be the range of the sequence. But since that is a set, so we know what is the meaning of a bounded set. So using that fact, we say that a sequence is a bounded sequence if its range is bounded, right? And a sequence will have if you look at a bounded sequence, then its supremum would be the supremum of its range, and the infimum would be the infimum of its range. So everything, when you're looking at a sequence, then just look at the range of the sequence and then see whether that set is bounded or not. If it is bounded, then you just uh, look at what is its supremum and infimum of the range, and you call it the supremum of the given bounded sequence and the infimum of the given bounded sequence respectively. Okay, so first you notice that if the range of the sequence is finite, then that means it is going to be a finite set, so it is always going to be a bounded set, so the sequence is always going to be bounded. Okay, so I have decided to give the definition of the limit also first, and then go on to examples, so that all the concepts will be cleared using each and every example. Okay, so suppose you are given a sequence. So notice I'm writing a sequence Sn here, meaning that even though I'm using the notation which looks the same as a singleton Sn, this is not the singleton Sn, it is the sequence Sn. So I could have used a subscript here n, but it looks slightly ugly, so I prefer to write it like this. So we want to say that it is convergent if I can find a number L in R, so that any open neighborhood of L would contain infinitely many terms of the sequence after a certain stage. So suppose I have taken this L is somewhere here, so I take a very small neighborhood of L. So that means I have to choose an epsilon which is positive, so that I can look at the interval L minus epsilon to L plus epsilon. Let me just mention this here because it came to my mind, that I don't remember whether I spoke of it before, that whenever I'm saying take a neighborhood, I'm mentioning generally an epsilon neighborhood, which means that the numbers are at a specific given distance from L, epsilon greater than 0. But you could have very well chosen, suppose I have the point 1, then the point 1 has a neighborhood point 1, open interval point 0.5 to 1.5. So if you look at open interval 0.5 to 1.5, that consists of all real numbers which are at a distance less than 0.5 from the number 1. So it is a 0.5 neighborhood of the number 1, but it is not necessary to take that. You could have an asymmetry type of thing. That is, suppose I took my open interval to be 0.3, to 1.6. Then this also is or zero point 0.3 to 1.2. Then this also is a neighborhood of 1. Only thing is that it is not symmetric. You're decreasing by 0.7 points. So any number which is less than 1 is at a distance less than 0.7, right? If you just start from 0.3 to 0.1, and if you take 1.2 on this right hand side, say for example, then the numbers which are greater than 1 will be at a distance of 0.2 from 1. So even 0.3 to 1.2 is also an open interval containing 1 and could very well have been chosen here to describe what we are going to say. But it is always easier to look at symmetry. And if recall that example which I was giving, that if I take from 0.3 to 1.2, inside that open interval 0.3 to 1.2, I of course have the open interval 0.8 to 1.2. So a similar, what is this open interval 0.8 to 1.2? That is the set of all real numbers whose distance from 1 is precisely less than 0.2. So you are getting a 0.2 neighborhood of the number 1, which is sitting inside the original one which you had chosen. So therefore, given any neighborhood, this we have discussed when we were talking about neighborhoods, but I want to stress it again here, that given any neighborhood, by neighborhood, suppose we take an open neighborhood, then inside that we will always be able to get such symmetric epsilon neighborhoods. So it is sufficient if we give our concepts using symmetric neighborhoods. So that is why whenever we are talking about such things, we are always going to say that take a symmetric neighborhood of the point. So if you want to take a symmetric neighborhood of the point, then it is sufficient to tell as to how far the points in the neighborhood should be. So I want all real numbers whose distance from this L is less than any given epsilon, positive. So therefore, when we are saying that given, now we are trying to say what it means by the sequence to be convergent, we mean that suppose I can find a real number L which satisfies this following property, that if you take any epsilon neighborhood of L, then this sequence which was going on S1, S2, S3, S4 and so on, see S1, S2, S3, S4 are the terms of the sequence. Their values may be the same, but whatever, we don't care about that. These sequences, this infinite sequence will have the property that you will be able to find a capital Nth term, so that after that term, starting from the capital Nth term, S capital N, S capital N plus 1, S capital N plus 2 and so on, they will all lie in the epsilon neighborhood of this point little l. So that is what we say, and I have used a purple color here because I wanted to stress this is a very, very important notion. So the sequence Sn is convergent if you can find this some number L which has the property that in any epsilon neighborhood of the number, or rather for any epsilon greater than 0, let us say it formally how we say, for any epsilon greater than 0, there is a positive integer capital N such that modulus of Sn minus L is less than epsilon for all n greater than equal to capital N. That is, the distance between the nth term of the sequence and L will be less than epsilon after capital Nth term. So for every little nth term after the capital Nth term, the distance between the value of the nth term and L will be less than epsilon. We will say that this sequence converges to L if this happens, and the notation to describe that the sequence Sn converges to L is the following. We just write limit. LIM is the shortened form of limit. So we write LIM and a n tending to infinity at the bottom of that, Sn equal to L. So this means precisely this. And sometimes casually it may be written as Sn tends to L as n tends to infinity. This is sometimes convenient when you are having an informal discussion. This number L is called the limit of the sequence Sn, and it is not clear beforehand that this number is unique. All we have said that if I can find such a number L so that this property holds, then we say that the sequence converges to L. But it may be possible that it converges to some other point also, but actually that is not true. If this number which we will get, it is unique, and therefore since by my prior knowledge, what I have done is I've used the uh, word the here, the limit of the sequence. So that means that there will be only one if the sequence converges. Okay, and there is one more terminology which is useful, and that is when L is equal to 0. That if you have a sequence which converges to 0, then we call it a null sequence. So this we will be using this terminology quite a lot. And finally, let us look at some examples. The first one is the one with which I had started. So let us look at Sn is equal to 1 by n for all n in n. So what is this sequence? I've tried to just picturize it here. If you put n equal to 1, then you will get 1, right? 1 by 1. If you put n is equal to 2, you will get half. Then you will get 1/3, 1 by 3. Then S4 is 1 by 4. S5 is 1 by 5, and so on. Sn is 1 by n, the general nth term, and so on. Right? So this is your sequence which I have depicted by a few of the terms precisely in blue, and the rest that there will be several terms I have denoted by blue dots. So you realize immediately that the range of the sequence, that is the underlying set of the sequence, is infinite, because for every n you have a 1 by n. So it is infinite, but it is a bounded sequence. Why is it a bounded sequence? Because if you look at any term, look at the nth term of the sequence, this is clearly greater than 0, and it is always less than or equal to 1, as you can see. So the underlying set is going to be a bounded sequence, bounded set. So therefore the sequence is a bounded sequence. Okay, so at least this much is clear, and we would like to see whether it converges or not. As you can very well guess that it converges by our picture. I have tried to show where it converges in purple. I have written this 0 in a purple shade to describe that this sequence is actually converging to 0. So you should be able to prove it. So what is the proof? That you have to take any epsilon greater than 0, and then you have to find a capital N positive integer, so that after the capital Nth term, the distance between the little nth term of the sequence and L will be less than epsilon. So in this case, that L is going to be 0 in this particular example. So first of all, for that you have to first of all take any epsilon greater than 0. So you do that. Suppose epsilon is greater than 0. So I have to find out some capital N so that the proper inequality holds. Now you notice that given this number epsilon and the number 1, if you use the Archimedean property of the real numbers, you will be able to get a positive integer, which I have denoted by capital N, keeping in mind the previous notations, so that capital N times epsilon is greater than 1. This is always true because epsilon was positive, so you keep on adding epsilon with itself. After a certain number of additions, you will be able to get a number which is greater than 1. That is your Archimedean property, so you are using it here. Now, suppose little n is greater than equal to capital N. Then what does that mean? That means that 1 by n is less than or equal to 1 by capital N. And 1 by capital N clearly is going to be less than epsilon, because capital N was so chosen, right? Capital N epsilon was greater than 1. So 1 by capital N is going to be less than epsilon. So what have you got? you have got that for all little n greater than equal to capital N, 1 by n is less than epsilon. Now, if you want to compare with your previous description in the definition of convergence, what you should have is 1, instead of Sn, you have 1 by n. So you have 1 by n minus 0, modulus of that should be less than epsilon for all little n greater than equal to capital N. But what is modulus of 1 by n minus 0? That is just modulus of 1 by n, and 1 by n is a positive number. So all you need to show is that 1 by n is less than epsilon for all little n greater than equal to capital N, and that is what you have done. For all little n greater than equal to capital N, 1 by n is less than epsilon. So that means modulus of 1 by n minus 0 is less than epsilon. So you have shown that whatever small epsilon neighborhood of 0 you take, something will be on the left. So it will be something like minus epsilon to plus epsilon. This minus epsilon to 0 will have no points. That's okay. But from 0 to epsilon, you will be able to, whatever epsilon you take, you will be able to get a capital N, so that these terms will get inside that particular neighborhood. So those terms will go beyond 1 by beyond epsilon on the left, right? So all the 1 by n's will become strictly less than epsilon. So they will be in the neighborhood minus epsilon to plus epsilon. Nothing will be on the left hand side of 0. That is fine. Everything will be on the right hand side, but it will be in the epsilon neighborhood. I think I have made it clear. So by your definition, you have seen that the sequence 1 by n is actually a null sequence. That is, it converges to 0. Okay, so let us look at one more example. So this is the nth term. So notice this is a style of expressing a sequence. We say let Sn be equal to some formula. So 1 plus minus 1 to the power n divided by n for all n in n. Right now we have this as our index set for all n positive integers. This means that you are actually describing a sequence whose nth term is given by this formula. So let us just plot it. Let us see what happens when n is equal to 0. Then, oh, I made a small mistake here. Since I have put minus 1 to the power n by n, so I should not have, and this is for all n in n. So I don't have n equal to 0. I was making a mistake. But suppose I put n equal to 1 here, then what do I get? 1 plus minus 1 to the power 1. So that is minus 1 divided by 1. So we get 1 plus minus 1. So that is this number 0. So this is the first term of the sequence. What is S2? S2 is 1 plus minus 1 to the power 2 divided by 2. So minus 1 squared is 1. So it becomes 1 plus half. So it is 3 by 2. So this is my second term of the sequence. So the first term of the sequence was 0. Second term of the sequence is 3 by 2. Third term of the sequence, what will it be? So you notice when n is odd, the numerator here becomes minus, right? So it will be, the third term will be 1 minus 1/3. So 1 minus 1/3 is what? 2/3. So this is the third term of the sequence. Now you can guess what is the fourth term of the sequence. It is 1 plus 1 by 4. So that is 5 by 4. I have plotted two more. So what is the fifth term of the sequence? It is 1 minus 1 by 5. So that is 4 by 5. And what is the sixth term of the sequence? That is 1 plus 1 by 6. So that is 7 by 6. And so on. So on has been depicted by these blue dots. So we keep on having these terms. So from 0, you go to 3 by 2, then 2/3, 5 by 4, 4/5, 7 by 6, and so on. So you'll just keep on going from the points uh, less than 1 to points greater than 1. And the way you are getting the sequence, these points are continuously getting closer and closer to 1, right? So I want to say, so that is why I have put this 1 as a purple number here, because I want to show that this sequence is actually convergent to 1. Before that, you notice that it is a bounded sequence. That is clear, because what is our Sn, the formula is this. So Sn minus 1 is just going to be minus 1 to the power n by n. So it is at a distance, maximum distance would be half from 1 on this side, and maximum distance would be 1 on the left of 1. So you get that Sn is between 0 and 3 by 2. You can very well see this. So therefore, this is a bounded sequence, first of all. And next, as I claimed, that I want to show that this is actually going to converge to 1. So let us see. Again, for that you have to choose some epsilon greater than 0, and then use the Archimedean property of the real numbers. Then you will be able to get a positive integer n, so that n epsilon is greater than 1. Okay, so now what do? You look at any little n greater than equal to capital N, and look at the distance of Sn minus 1, the distance of Sn from 1. So that is the modulus of Sn minus 1. But Sn minus 1 was what? Minus 1 to the power n by n. So if you take the modulus of this, see, minus 1 to the power n by n is a negative number if n is odd, and it is a positive number when n is even. So whatever it is, if you take the modulus, you will always get the positive number 1 by n. So if I choose my little n to be greater than equal to capital N, then 1 by little n is going to be less than equal to 1 by capital N, and 1 by capital N is going to be less than epsilon. So what have you got? You have got that if you take your little n greater than equal to capital N, then modulus of Sn minus 1 is going to be less than epsilon. So if you take an epsilon neighborhood of 1 here, there will be a term capital N, there will be a term S capital N. So you will get a nth term, so that after that term, every term of the sequence will lie in that small epsilon neighbor around 1. That is what you are proving it from here. So that by definition means that limit n tending to infinity Sn is equal to 1. I hope this is okay. So one more example which is useful but not so difficult to see at all. That is, if you fix up a little c belonging to R and take a sequence where Sn is taking the value little c for all n. That means what? You have an infinite sequence, S1, S2, S3 and so on. But your first term has value c, the second term also has value c, the third term also has value c, and so on. So the sequence is c, 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 and so on. So the range of the sequence is what? It is just a singleton c. So it is a finite set, clearly it is bounded, no problems. And you look at, don't even bother about choosing epsilon neighborhoods and so on. If you take any term of the sequence Sn, then its distance from C is obviously 0, because the term of nth term of the sequence has value C. So modulus of Sn minus C is exactly equal to modulus of C minus C. So it is going to be 0 for all n. So therefore, if you take any epsilon greater than 0, then modulus of Sn minus C is going to be less than epsilon, because epsilon is greater than 0 for all n. So for n greater than equal to 1, right? So in your definition, now what is happening is you're looking at mod Sn minus C. So that mod Sn minus C is 0. So that will be less than epsilon. And what for any epsilon. And what is your capital N? You have to choose one capital N, that is just 1. So for all little n greater than equal to 1, modulus of Sn minus C is going to be less than epsilon. This is true for any epsilon greater than 0. So therefore, the sequence is actually convergent to the point C. That is what you expect, right? All the values are going to be hitting just the point C. So the sequence has to converge to that point. So such a sequence is called a constant sequence for obvious reasons. The terminology is quite clear. So we do have these sequences. And if a sequence is not convergent, then we say that it is a divergent sequence. Now, once it is a divergent sequence, there are many things which can happen. There is a specific uh, property which the sequence should hold, so that it is a convergent sequence. But if it is not convergent, that the property can fail at many levels. So therefore, when you are looking at a divergent sequence, there are going to be several types of things which are happening. So first of all, it may happen that you have these sequence terms of the sequence S1, S2, S3 and so on. It may happen that whatever k greater than 0 you take, you will be able to get a capital N positive integer, so that after the capital Nth term, every term of the sequence becomes greater than k. This is true for every k. Suppose that for any k greater than 0, you are able to do such a thing, that after a certain term, every term becomes greater than k. Then we will say that the sequence is divergent to infinity, and in that case we will write it as this limit n tending to infinity Sn equal to infinity. Even though we are writing equal to infinity, this statement just means this. Infinity is not to be treated as a number here, even when we are writing equal to infinity. Limit n tending to infinity Sn equal to infinity means precisely that for any k greater than 0, you will be able to get a capital N positive integer, so that every term of the sequence after the capital Nth term is greater than k. If this happens, then we say it diverges to infinity. So once you have the notion of diverges to infinity, obviously you can expect that there will be a similar notation of diverging to minus infinity. So what is the argument there? When will we say that a sequence is diverging to minus infinity? If however small a number you take, so for any k less than 0, if you are able to get a positive integer capital N, so that for every term after the capital Nth term, Sn is less than k, then we will say that it is diverging to infinity, minus infinity. And again, as before, we will write limit n tending to infinity Sn is equal to minus infinity, with the same caveat, same warning, that minus infinity here is just used to describe this whole sentence in a short form. It is not a real number, it is not considered as a number. So if a sequence diverges to infinity or diverges to minus infinity, then we say that the sequence is properly divergent. So at least some nice behavior is happening, even though it is not converging to a particular point. At least it keeps on increasing in this case, or it keeps on decreasing in this case in some sense, right? In some sense, notice that it is not as if your terms keep decreasing. It is the value of the terms which keep decreasing, right? So keep that in mind always. It may be that your Sn plus 1 is not less than Sn, but when you look at Sns, then the values of those terms, they will be keep on getting less than any negative number k which you choose. Then we are saying that it is divergent to minus infinity. So at least this behavior is also something, it's not as good as convergence, but it is good. So we describe such sequences as properly divergent because it is behaving in some systematic fashion. If a sequence is not convergent and it is also not properly divergent, such sequences are called oscillatory sequences. So oscillatory, this term comes from exactly oscillation, which was used in the beginning, but then there were examples of many sequences which were not properly divergent and which were not oscillation in the real sense of the word. Oscillation, remember, is used as a term when we are talking about pendulums. So in pendulums, you are just oscillating between two numbers. So even if it is not two numbers or anything like that, if that was the first example which one had considered. So the terminology comes from there, that it is any sequence which is not properly divergent is an oscillatory sequence. But it now encompasses all these, and there are many examples of not properly divergent sequences which will not exactly in the classical sense oscillate between 2 points. Okay, so to understand these notions a little bit better, we'll look at some examples. Before that, notice one thing, that when you're talking about diverging to infinity and diverging to minus infinity, it should strike you that suppose I take a sequence which diverges to infinity, And if I put a take the negative of those terms, so instead of Sn, if I take minus Sn, and suppose the sequence is diverging to infinity, then the sequence minus Sn will automatically diverge to minus infinity. So why am I saying this? That this is actually useful also. And if you want an example of a sequence which diverges to minus infinity, just look at an example where the sequence is diverging to infinity and then multiply each term of the sequence by minus 1. You will get a sequence which diverges to minus infinity. So having said that, let us look at examples. So as I said, sequence is described by its nth term most of the times. So we just write let Sn equal to n squared for all n in uh, the set of positive integers. So what is the sequence going to look like? We have tried to plot them. So if S1, you look at S1, that is just 1. S2 is 2 squared, so that is 4. S3 is 3 squared, so that is 9, and so on. So Sn is going to be n squared. So it is obvious, so let us not waste too much time on this giving a exact description as to why, but this first of all, the range of the sequence is infinite, that is clear, and it is also diverging to infinity, correct? So it keeps on increasing. Whatever k you take, you will be able to get a number of the type m square, a square which will be greater than k. This is always possible. So it is going to diverge to infinity. And as I said, that you can use this example to get a sequence which is diverging to minus infinity. Just look at the sequence Sn equal to minus n square. So that will become what? That will become minus 1, minus 4, minus 9, etc. minus n squared. So that is a sequence which is going to diverge to minus infinity. Okay. Next, let us look at another example. Sn equal to 1 plus minus 1 to the power n for all positive integers little n. So what is happening here, you notice, what is S1? S1 is 1 plus minus 1. So that is 0, right? So that is plotted here. What is S2? S2 is 1 plus minus 1 whole square. So that is 1 plus 1. So that is 2. So notice that this minus 1 to the power n is going to be minus 1 if n is odd and 1 if n is even. So Sn is always going to take the value 0 when n is odd, which we have shown in the picture, and it is always going to take the value 2 when n is even. So how does your sequence look like? It is a classical sequence which is going to give you an oscillating sequence. You start with S1, so it is 0, then S2 is 2, then S3 is again 0, S4 is 2, S5 is 0, S6 is 2, and so on. So you keep on oscillating between 0 and 2. This is your sequence. So if you write down in details, it is just 0, 2, 0, 2, 0, 2, and so on. So this sequence will have its range as a set consisting of only 2 points, because those are the 2 points which are the values of the uh, sequence terms. So you just get the range as 0, 2, which is a finite set 0, 2, which is a finite set. Therefore, it is a bounded sequence, no problem. And we want to say that it is not going to converge. So let me just explain it here once, and you will see why. Suppose it converges to, if you want to see that it converging to something, then that something has to be a real number, which can be either 0 or 2, or something which is not 0 or 2. So if it is not 0 or 2, it can be anywhere. So I have just drawn in an x in between. So notice that I can always get a small neighborhood of x which contains neither 0 nor 2. Since if x is not equal to 0 and if x is not equal to 2, then the distance between 0 and x and 2 and x is going to be positive. So this we have this type of argument we have seen many times. So I hope it is clear to you by now that if x is a number which is different from 2 and 0, then you will be able to get a neighborhood of x which will not contain the point 0 and 2. So what happens in this particular case, that you are able to get a neighborhood of x which will not have any terms of the sequence. So if you are able to get a neighborhood which does not contain any term of the sequence, obviously this is not going to be a limit point of the sequence, right? It is not going to be the limit of the sequence, sorry. So if you want that this sequence should converge, that convergent point or the limit of the sequence cannot be different from 0 or 2. But what happens with 0 and 2? So for example, look at 0. Then what is happening is, whatever you can, first of all, 0 is a different number from 2. So you can choose a neighborhood which is not containing the point 2. Like in the picture, I have shown a small neighborhood. It could be larger also. Only condition I'm putting is that 2 should not be in that neighborhood. So then what is happening? S1, S3, S5, S7, and so on, all these odd terms of the sequence are going to lie in this neighborhood. So the neighborhood of 0 has infinitely many terms. That is perfectly all right. But what was your definition? Your definition was that you should be able to get a neighborhood of L, so that after a certain term, every term of the sequence belongs to the neighborhood of the point L. So here what is happening in our example is that there are infinitely many terms of the sequence which are in the neighborhood of 0. But it is not happening that after a certain term, every term of the sequence is there, because whenever you are looking at an even term of the sequence, term which is indexed by an even number, then that term is not here. So S1, S3, S5, S7, etc. are here, but S2, S4, S6, S8, and so on, they are all outside this neighborhood. So you will not be able to get a capital N positive integer, so that after that positive integer, after the capital Nth term, every term of the sequence is in the neighborhood of 0. That is not possible. You are getting infinitely many terms of the sequence here, but that is not sufficient. That is what I am trying to stress. You want that every term of the sequence after a certain term should lie in the neighborhood. That is not possible, because every time you get a term of the sequence which is indexed by an even integer, it goes outside the neighborhood, right? It is just oscillating between these two things. So therefore there is no question of 0 being a limit point of this sequence. Similarly for 2, this, take any neighborhood like this of the number 2 which does not contain 0, right? So in that neighborhood you will have infinitely many terms of the sequence, but again you will not be able to get a capital N positive integer, so that every term of the sequence after the capital Nth term lies in 2, because every sequence which is indexed, every term which is indexed by the odd integer, odd positive integer, is going outside the neighborhood. So I am at least able to get such neighborhoods which are not satisfying the property required, and therefore 2 will not be a limit point. You can say that we could have taken a huge neighborhood which would contain both 0 and 2, then there would have been no problem. But that is again not the issue. The issue is that for any epsilon greater than 0, you should be able to do this. So for however small or big or whatever neighborhood you take of the point L, this condition in purple should be satisfied. So in our example, we are able to get some neighborhoods where the condition is not satisfied, therefore it will not be a limit point. There may be a neighborhood for which the condition is satisfied. That is not sufficient. You should be able to get a neighborhood, you should be able to show that the condition is satisfied for every neighborhood. I hope I have made it very clear that this sequence is not going to converge. It is not a convergent sequence. In fact, it is a oscillating sequence, and it is a finitely oscillating sequence because the range of the sequence is a finite set. Okay, so let us look at another example, which is given by S2n is equal to n and S2n minus 1 is equal to 0 for all n. So what is happening? What is S1? S1 is 0, then S2 is 1, S3 is 0, S4 is 2, S5 is 0, and so on. So every you keep on increasing when you are looking at the even indexed terms of the sequence, and every odd index term is coming back to 0. So you just go 0 to 1, then 0 back, then 2, then 0, then 3, then 0, then 4, and then 0, and so on. So this is the way you are getting the sequence. Again, if you think about it, then this sequence is not going to converge anywhere. For similar reasoning, there is a there is a positive distance between these terms. So whatever number you choose from here, if you take a small neighborhood of that, it will not contain uh, terms of the sequence after a certain term, including this one. For the same reason, there is no even indexed term going to lie near 0. They are all going further and further away. So therefore, this is not a convergent sequence. It is also not diverging to infinity. Notice, because every time you're coming back to 0, it is not as if you take any k greater than 0, then all terms of the sequence after a certain term will be greater than k. That is what you wanted, right? It will diverge to infinity if for any k you will be able to get a positive integer n, so that Sn is greater than k for all little n greater than equal to capital N. That is not happening here. Always you are getting back to 0, right? Every odd term comes back and hits 0. So this sequence is also not going to diverge to infinity, even though the value of the terms of the sequence keep increasing. But since there is this reversal back to 0 at every odd place, so it does not diverge to infinity, and in fact it is an oscillating sequence. The way I was showing you, see that it is a oscillating. It goes from 0 to 1, back to 0, then 2, then back to 0, and so on. So it is oscillating. The range of the sequence is infinite, so it is an infinitely oscillating sequence. Okay. Apart from this, I would just like to mention one sequence which is very useful, uh, and people have been studying it quite a lot, uh, which is the Fibonacci sequence. And how is it described? It is described recursively. So S1 equal to S2 is equal to 1. This is what is given. And then after that, Sn is defined to be Sn plus 1 plus Sn minus 2. So we have plotted some terms. So S1 is equal to S2 is 1. S3 is what? S1 plus S2. So it will be 2. What is S4? That is 2 plus 1. So it is 3. S5 is what? 3. S3 plus 2. So it is 5. S6 is 5 plus 3. So 8. S7 is 8 plus 5. So that is 13. And so on. So this sequence is clearly not bounded, that is obvious, and it is actually diverging to infinity. It is clear here. It keeps on increasing and it diverges to infinity. So this is called the Fibonacci sequence. It is used in many places, as you might have seen. There are many applications, and as a homework you could always, for those who have not seen this, you could go and search the net. You will see some very beautiful pictures which are related to the Fibonacci sequence. Okay, so here I want to make an important observation. We have looked at several examples. Notice that uh, in the definition you are always saying that convergence or divergence or whatever we are saying that after a certain term something should happen. So what is happening in the beginning of the sequence, in beginning few terms of the sequence, is not important. If you manipulate a little bit, say for example, if you have the sequence uh, 1/2, 1/3, 1/4, etc., you saw that this converged to 0, right? Instead of that, suppose you look at the sequence 1, 2, 3, 4, 5, 6 till say 5000, and then the 5001th term is 1 by 5001, 1 by 5002, 1 by 5003, and so on. So what you're doing is you're describing the sequence as n, Sn is equal to n till n is equal to 5000, and then you're saying that Sn is equal to 1 by n for n greater than 5000. So it becomes 1, 2, 3, 4, what I said, till 5000, then 1 by 5001, 1 by 5002, and so on. What can you say about this sequence? This sequence will also converge to 0. In the beginning, it is increasing, right? It is going on from 1 to 2 to 3 to 4 until etc. till 5000. So it would look like that it is going further and further away from 0. But then suddenly it becomes 1 by 5001, 1 by 5002, 1 by 5003, and so on. So it starts coming closer to 0. So you want whatever neighborhood of 0 you take, after a certain term, the terms of the sequence should go and sit inside that neighborhood. That will happen after the 5000th term. So you will have to look for that capital N positive integer which is greater than 5000. You will not get it before that, because before that the sequence terms were increasing at a unit at every stage, right? So that when you want to, that particular sequence is also going to converge to 0, but the capital N which you will get for every epsilon greater than 0 is going to be a big number, which is going to be greater than 5000 at least. So even if you manipulate the first finitely many initial terms of the sequence, that is not going to affect the convergence or divergence of the sequence, because in the definition itself you see that you just want that something should happen after a certain term. So what is happening before that term is immaterial. It could take any sorts of values, but if it starts behaving in a certain fashion after some term, then that is sufficient to observe whether the sequence is convergent or divergent. So as we see more and more examples, I hope this particular point will become clearer. I just want to do a few results after this. So first one is, which I said in the very beginning, that limit of a convergent sequence is unique. So how do you see that? You suppose that Sn is a convergent sequence, and suppose limit n tending to infinity Sn is equal to L. Then I want to say that L is unique. For that, what I do is I choose any real number m which is not equal to L, and I will show that m cannot be a limit point of Sn. So that is sufficient to say that the limit of this sequence is a unique number L. Okay, so I have taken any real number m which is different from L, m not equal to L. Then the distance between L and M, that is modulus L minus M, is going to be a positive number. So I have called that positive number something R. Okay, so now we know that for any epsilon greater than 0 something should happen. So instead of for that epsilon you choose this R. Okay, so for this R also, since limit n tending to infinity Sn is equal to L, we will be able to get a positive integer n, so that the distance between Sn and L, that is mod Sn minus L, is less than R by 2. This is for deliberate. I have not taken R, but I have taken R by 2 for a ease in calculation. So I will be able to get a positive integer n, so that for all little n greater than equal to capital N, mod Sn minus L is less than R by 2. So then what happens? Then look at the distance between Sn and M. Modulus of Sn minus M, that is going to be greater than equal to modulus of L minus M minus modulus of Sn minus L. Why? Because you know that if you just look at modulus of L minus M, then you can write here as mod L minus Sn plus Sm minus m. So that by triangle inequality is less than or equal to mod Sn minus m plus mod Sn minus L. So therefore, if you rearrange, you will get mod Sn minus m is greater than equal to mod L minus m minus mod Sn minus L. This is clear. Just write minus Sn plus Sn here and use triangle inequality and rearrange, you will get this inequality. Now what do you know about this? L minus m, modulus of that is exactly equal to R. So this is R minus modulus of Sn minus L. So that is going to be greater than R minus R by 2 after the nth term. So for all little n greater than equal to capital N, modulus of Sn minus m is greater than R by 2. So that means that if you look at the R by 2 neighborhood of m, that will not contain any term of the sequence after the capital Nth term. So that means that the sequence Sn cannot converge to m. If it had to converge to m, any neighborhood of m should have contained infinitely many points of the sequence after a certain term, but that is not happening here. Let me just give you a geometric explanation of this, which will make it clear. You have this sequence Sn plotted on the real line and it is converging to L. So if you take an R by 2 neighborhood of L and a R by 2 neighborhood of M, they will be disjoint where the distance between L and M is R. Now every sequence, every term of the sequence is going to lie in the R by 2 neighborhood of L. So automatically it will not lie in the R by 2 neighborhood of M. So therefore it will not converge to M. So the limit of a sequence is going to be unique. So I had thought of talking about a little bit more in this particular lecture, but we will not, and that I will do in the next lecture maybe, and we will do some more examples. The set of recommended books is the same. So we stop here for the time being, and in the next lecture we will continue.